modeling the synchronous machine, and in the last lecture we had derived equations in the synchronous reference frame for the machine. Synchronous reference frame is also the rotor attached reference frame for the synchronous machine, because the rotor of the synchronous machine rotates at synchronous speed. And since in the rotor of the synchronous machine there is a source of excitation, we attached the synchronous reference frame axis accordingly. The axis along which the main field of the alternator exists is then the D axis, and the axis 90 degrees to that is the Q axis. Historically, the machine analysis field had developed starting from the synchronous machine, and the direct axis has always been identified with that of the main field, and the Q axis has been identified with an axis that is 90 degrees to it. It is only subsequently that the machine analysis methods were applied to the induction machine also, and it is only beyond the 1960s that these machine equations were used for doing machine control of the induction machine. So, that is what we have been looking at. We have been seeing the synchronous machine modeling in the synchronous reference frame, and in the later part of the last lecture we looked at referring the rotor variables also to the stator number of turns in the synchronous reference frame, and we were seeing how the equations simplify as a result of that. So, let us look at those equations again. We start with the synchronous machine equations. You had Vds, Vqs, V0s and V field. Instead of writing an elaborate description, we will combine all of them into an operational impedance matrix. So, that makes it a little more easy to write. So, this is the D axis applied voltage, which consists then of a stator resistance drop and then plus the direct axis synchronous inductance P, where the direct axis synchronous inductance is then going to consist of a leakage inductance of the stator plus 3/2 times LD, which we then called as LMD, which is the magnetizing inductance, 3-phase magnetizing inductance along the direct axis, and this together is then the D axis synchronous inductance. So, that is what we had, and then here it was minus LQs into omega s, where LQs is defined as the leakage inductance of the stator plus 3/2 times LQ, this being defined as LMQ, and then this together is then the quadrature axis synchronous inductance. And then there is no contribution here from the 0 axis term, and then there is a D axis speed EMF that is induced, which was root of 3/2 times MSR multiplied by omega s. So, that forms the last entry. Here what you have is L ds times omega s and then Rs plus Lqs into P, and then you have this is Q and 0, so 0 here, and then there is no Q axis induced EMF, sorry, this is along the direct axis, so this is P, and then here you have the speed EMF, so this is root 3 by 2 into MSR into omega s, and then along the 0 axis Rs plus LLs into P, there is nothing there. Here you have root 3 by 2 into MSR into P. There is no speed EMF term because this is not a fictitious coil, and then on the 0 sequence term there is nothing here, and then you have Rf plus Lf into P. So this matrix multiplies IDS, IQS, I0s and I field, where Lf is the self inductance of the field on the rotor, that then consists of a leakage inductance and then a magnetizing inductance of the field. Now we started in the last lecture to refer the rotor variables to the stator turns, and when we do that we said that it is referred to the stator turns under the assumption that if you now look at the d axis has the field coil, this is on the rotor, and then it has a fictitious coil derived from the stator, that is the ds coil. So this is ds coil and this is the field coil, and since these two lie along the same axis, we assume that the flux that is linking the field links the ds coil also, and if you now multiply the mutual inductance by the ratio of number of turns, what you get is the magnetizing inductance along the d axis, which we then called as, which is the same as LMD, that is the magnetizing inductance along the d axis. So with that what happens is the Vf dash becomes the referred stator turns referred field voltage, and here what you get is 3 by 2 times MSR into the turns ratio, which then becomes LMD. Similarly here you get LMD into P, and this becomes LMD into omega s. Now as far as the field is concerned, you get a turns ratio from replacing If by If dash, and another equivalent term comes by replacing Vf by Vf dash. So you get turns ratio squared in this term, which then means Rf is referred by the turns ratio squared to the stator turn, so it becomes then Rf dash, and Lf becomes referred by the turns ratio squared, which is again Lf dash. But in Lf dash what happens is the leakage inductance gets referred by turns ratio, so Lf dash is nothing but LLf dash, which is LLf multiplied by the turns ratio squared into 3 by 2 of course. LMF is the magnetizing inductance of the field, and when you multiply that by the turns ratio squared, what you get is the magnetizing inductance of the d axis coil, and therefore this is nothing but LMD. D here. So, LF dash is LLF dash plus LMD, where LMD is then given by this expression. Along with this, we then also have the expression for the electromagnetic torque. Torque was given as IDS into IQS into LDS minus LQS plus root 2 by root 3 by 2 MSR into IF into IQS. Now that you replace it by the stator referred turns, this term becomes then LMD in IF dash here. So, these are the equations referring the machine to the stator turns and in the synchronous reference frame. In this description, we have assumed that damper windings, damper bars have not been considered here. We saw in the beginning of the lectures on alternators that if you look at the alternator poles, if this is the alternator pole and then you have the coils of the field that are wound here, what we said was in the pole face you have bars that are introduced which run along the length of the pole, and these bars are all shorted here, shorted on this side, with the result that if there is going to be any change in the speed from synchronous speed, either more or less, then there will be induced EMF in these bars and there can be currents that flow in these bars, and the shorting ring connects it to the bars on the next pole face. So, there is going to be flow of currents all around, and this causes the loop that thereby forms here causes a source of excitation along the Q axis, and definitely there are loops formed here which cause a source of excitation along the D axis, and therefore because damper bars are there, it will affect the machine model by providing sources of excitation both along D and Q, and therefore that is represented as follows. Let us draw the stator axis. So, this is your AS axis, BS, and then the CS axis, and then you have the rotor axis. So, let us say this is the axis of the rotor. So, you have the rotor angle, and in the along 90 degrees to this axis you have the quadrature axis of the rotor. So, this is your D axis and the Q axis. What we had done earlier was you had the DS axis, DS excited, which is the stator winding converted to the synchronous reference frame, which gives you a DS and QS coil. This is QS coil. Apart from this, in the model that we had written down, we had a field excitation which was there along the D axis field. Now, if one wants to account for the presence of dampers, one has to consider at least one more coil on the D axis, which is a representation of the field that is generated by currents flowing on the D axis. Due to this, and one more coil at least on the q axis, which accounts for the MMF that is generated along the q axis. Now since these are always shorted by the shorting rings, we normally consider these two coils to be shorted, and the normal symbol that is used to represent these two are KD coil and KQ coil. So if one is now going to include the effect of KD and KQ, how do we modify this system of equations that we have derived so far? So if one has to do that, remember we are going to write down the equation in the synchronous reference frame, and we make use of the fact that we are writing these equations in a stator referred way. That means we have already done this exercise where Vf is replaced by Vf dash, If is replaced by If dash, and so on. Similarly, there will be flow of IKQ in this coil and IKD in this coil. There are certain number of turns here and certain number of turns here, and when you refer everything to stator turns, then the equations really become easy to write. To modify that, let us extend these set of equations. Let us extend this set of equations. What we are now going to have is, in addition to all this, you have a VKD dash and a VKQ dash. So we augment the first equation set by adding these two rows. This is extended. Now what happens as a result of this? We know from the way in which we have analyzed or derived these synchronous machine equations, and indeed the generalized machine equations valid even for the induction machine, that the terms here are of different varieties. One is the stator, the self coil resistance terms and the self coil inductance terms, and then the mutual di by dt terms, and then you have speed EMF terms. Now self coil resistance terms are bound to be there, and they will always occur along the diagonal like this. Self coil inductance terms will always be there, they will also occur along the diagonal in this manner. Mutual di by dt terms, we have seen that they will occur between one coil and another coil, provided they lie along the same axis. For example, here if you take voltage of the d axis term, you have a mutual inductance due to the field coil, which was the mutual between this ds and f. Now you have one more coil Kd, this will also cause a mutual inductance, and because we are now writing it in a stator referred manner, you remember that mutual inductance multiplied by the ratio of number of turns gives us the magnetizing inductance, and that magnetizing inductance is along the d axis, and therefore if we want to include the effect of Kd coil on the stator voltage stator d axis equation, it will arise as an Lmd multiplied by P. And then you have speed EMF terms. Speed EMF terms arise in one coil, provided it is a fictitious one, from the excitations on the axis 90 degrees away. Now in this case Kd is, I mean we are looking at the equation for the ds term, and this coil is definitely a fictitious coil because it is a representation of actually fixed coils on the stator. We are moving away to the synchronous reference frame, and therefore it is fictitious, and therefore this will have speed EMF terms, and speed EMF terms will arise due to coils that are in the axis 90 degrees away, and you already have one speed EMF term, that is minus LQS into omega s due to the QS coil, and now you need to provide another speed EMF term due to the KQ coil, and therefore this is LMQ into omega s. Now the speed EMF term arising due to IQS is, this is actually a source of excitation that is present in the stator itself, it is not on the rotor, and therefore the inductance term that arises in the speed EMF term is the stator inductance of the Q axis, whereas here this coil is present on the rotor, and therefore the term that comes here is the magnetizing inductance or the mutual inductance between the stator and the rotor. So that is what is going to come here, and then we examine what is going to happen in the Q axis coil of the stator. So Q axis coil of the stator will then have a speed EMF term due to the D axis on the field on D axis on the rotor, which will then be LMD into omega s, and then between the Q axis stator and the Q axis damper you would then have di by dt term, so that is LMQ into P. The 0 axis is not affected by this operation, so those two will be 0, and then you have VFD, which is the equation for the field coil. So the field coil is actually on the rotor, so it is not a fictitious coil, therefore it will not have speed EMF terms, it will not have di by dt terms due to excitations 90 degrees away, but it will have di by dt terms connecting these two, and of course its own self term which is there. So this is your D axis column for KD axis, and this is your KQ axis column, and therefore the field with the KD axis will then have an LMD into P, with the Q axis it would be 0, and then we come to the D axis equation, that is KD equation. So this along with the direct axis would have an LMD into P, they are on the same axis. With respect to the Q axis of the stator there is not anything because this is not a fictitious coil, it is directly on the D axis, and then with respect to the 0 axis term there is nothing. With respect to the field it has an LMD into P, and then with respect to this one you have RKD, this is the self term, so there is a resistance of the damper and then a self inductance of the damper referred to the stator turns, and then with the Q axis of the damper there is not any term there. So similarly here this would be 0, you have LMQ into P, with the 0 axis term there is not anything, and then this is with the field, so there is no term here. With the D axis there is no term here, here you have RKQ dash plus LKQ dash into P. So the matrix is this matrix is then multiplied by the vector of currents, so that is assumed to be present here. Let me not write that again. So that is IDS, IQS, I0S, IF dash, IKD dash and IKQ dash. So that then is the model of the synchronous machine, having one coil to represent the damper along the D axis and one coil along the Q axis, referred to stator turns. And as usual, one can write the expression for torque by using the relation I transpose Gi. You have to separate out the speed EMF terms into the G matrix and then multiply it as I transpose Gi, one gets the torque. So you can see that if you want to augment the description by having more coils to represent the damper windings, some more coils if you want. Now those can be added very easily by understanding how this representation is. There is one more aspect that I think I have missed, the speed EMF term here is negative. So that is then the synchronous machine equation. One can look at developing this in terms of flux variables, and let us look at how it can be written in terms of flux variables for a simpler description, not having this elaborate form. So to develop these equations or to represent it in flux variables, we will again neglect the damper windings, neglecting damper because it is just simpler to write. Otherwise one can still define the flux linkages as psi ds, which is the flux linkage of the stator winding along the D axis, is L ds times IDS, that is the self inductance direct axis synchronous inductance multiplied by IDS plus LMD into IF dash, the mutual inductance multiplied by the field current stator referred with respect to turns, and then you have LMD into I KD. I think following our notation we should be consistent, so let us put all the rotor variables as superscripts. So this will be KD dash and KQ dash, so IKD dash. If there are more representations along the D axis for the dampers, then you would have this as KD dash 1 and then maybe IKD dash 2, IKD dash 3 and so on. So that would be the form, and similarly psi QS would be written as the quadrature axis synchronous inductance multiplied by IQS. There is no field along the Q axis in the rotor, so after this there are only the dampers, and therefore LMQ into IKQ dash. If there are more representations for the damper, you will have more such terms. So to develop the equations in the flux variables, let us consider a simpler form. We will neglect the damper bars, and therefore we are going to consider only a subset of these equations, which is up to this. So that expression can be written as VDS is RS plus LS L, how have we written DS, LDS into P into IDS plus minus LQS into omega S into IQS, and then plus LMD into P IF dash, and then you have VQS is LMD into omega S into IDS plus Rs plus LQS into LQSP into IQS, and then plus LMD omega S into IF dash. So, that is the equation for the stator, and what we see here is you have LDS into IDS. So, let us rewrite that. VDS, we will take the stator resistance term out, so that is LS into IDS, and then you have LDS into IDS plus LMD into IF, which is the same as your stator d axis flux linkage. So, that can be written as P times psi ds, and then you have minus LQS omega s into IQS. LQS into IQS is psi QS, that is what we see here. Psi QS is LQS into IQS, and therefore you have minus omega s into psi QS, and then we write the expression for VQS, that is again Rs into IQS, and then you have LS IQS, LQS IQS, which is nothing but therefore P times psi QS, and then you have omega s times psi ds. So, this is a simpler representation of the machine equation represented by flux variables. This is often used in order to do computations. With this, the expression for the generated torque is IDS into IQS into LDS minus LQS plus LMD into IF dash into IQS. So, this is what you have. This can be written as, now let us split the terms, IDS IQS into LDS minus IDS IQS into LQS plus LMD into IF dash into IQS. Now, these two terms together, one can combine this, and you see that that can be written as IQS multiplied by LDS into IDS plus LMD dash into IF dash minus IDS into LQS IQS. Now, this term is nothing but your psi ds as we have defined, and therefore, this can be simplified as IQS into psi ds minus IDS. This term is nothing but psi QS, so that is psi QS. So, torque can again be written in terms of product of flux into flow of I. So, these are different ways in which one can represent the synchronous machine equations, which is useful for study. Though we have been representing the electrical equations and the expression for T, in order to describe the dynamics of the system, one must not forget that you need the mechanical equation also, and the mechanical equation takes the form generally, this is your generated torque. Remember, again all the equations that have been written are being written with motor convention. We may be analyzing synchronous machines normally when we study the first course on electrical machines. Synchronous machines are not studied under this convention, they are studied using the generator convention, whereas we have used this convention in order to maintain the continuity of what we had started as induction machines, and indeed nowadays there are synchronous machines that are being used for control purposes, at least as synchronous motors, in which case this is a convention that one would be using to study these machines. And therefore, using this convention, the generated TE is output from the machine, it is a mechanical output. So this mechanical output minus the load torque is going to result in an increase in speed. Load torque may then consist of a fixed component and in addition viscous friction drag components, which are to the exponent of omega 1, omega power 1 or omega squared and so on. So all those terms are going to come into TL. So we have been looking at lot of these machine equations, how to develop these machine equations and so on. However, if you look back on whatever we have done, we have not made any reference to the conventional way in which you would look at a machine, let us say in a first course in induction machine. The first course in induction machine normally starts or deals with the steady state analysis and starts by developing equivalent electrical circuits. For example, if you take the induction motor, what you would do is to study the induction motor you would develop an equivalent electrical circuit, which is a per phase electrical circuit, and that electrical circuit is developed based on an understanding of how the machine would work, namely you have a rotating magnetic field and then you have therefore some currents flowing in the rotor, and that voltage induced in the rotor depends on the number of turns and therefore so on and so forth, right. Whereas here in the development that we have done, we have not made any reference to the equivalent circuit of the induction machine at all. We have directly started by assuming that the stator of the induction machine has 3 phases distributed in a certain manner, and then we found out an expression for distributed winding inductances. We have developed it from a totally different angle. So what is then the relationship between whatever we have derived now and what we have understood from the first machines course regarding the equivalent circuit and the performance of the induction machine? So do these two match at all? Will this give the same equivalent circuit that what we have been using in the first course on electrical machines? I am sure some of you would have had this doubt. So let us look at how to do steady state analysis before we make use of this equation for more sophisticated applications. We need to understand that these equations indeed boil down to what we have been studying in the first course when we did steady state analysis. So that is what we will now look at. When we say steady state analysis, what we automatically assume is we are looking at sinusoidal steady state analysis. That means the voltages that are applied to the machine are pure sinusoids, and therefore the responses flow of IAS or IBS, ICS, they will also be pure sinusoids, and you do not have any speed variations, right. So this means that speed has settled down, both voltages and currents are pure sinusoids, current transients have settled down, have gone to 0, no disturbances. So everything is a nice sinusoid that is there. So let us look at the induction machine equation. So let me write down the equations in the synchronous reference frame. you have VDS, VQS, VDR and VQR. Remember that when we are using a balanced excitation, 0 sequence is absent, and therefore we need not really represent the 0 sequence. Most cases of machine analysis, 0 sequence may indeed be neglected since it is balanced. Here you have Rs plus Ls into P, omega s into Ls, and you have Lm into P, Lm into omega s minus omega r. Now that we have just now finished the synchronous machine modeling, it would be appropriate to draw your attention to these two terms. There is no LMD and LMQ here, but just an LM. This arises because the induction machine has a perfectly cylindrical arrangement in the rotor. There is no saliency, and therefore you do not have LMD and LMQ coming here. And then you have minus omega s Ls, Rs plus Ls into P. Similarly, here there is no direct axis synchronous inductance or the quadrature axis synchronous inductance, it is just the self inductance of the stator. R minus Lm omega s into P so this would then be the machine equation with IDS, IQS, IDR and IQR, similarly VDR and IQR. So that is the machine equation. Now the equivalent circuit of the induction machine, as we draw in the normal way, refers to the per phase equivalent circuit. Per phase equivalent circuit in the stator reference frame, that is then the actual phase variables that are applied. So we have to transform these equations into the normal ABC reference frame. And how does one do that? We have VDS, VQS, V0s and so on. So if you want to transform those equations, you have VDS, VQS, V0s is of course 0, so we need not really consider that. So let us look at VDS and VQS, and this has to now be transformed to the alpha beta reference frame and then the 3 phase frame. So how to transform VDS and VQS to the alpha beta frame? You remember that the transformation VD VQ from alpha beta was cos theta and then sin theta minus sin theta and cos theta. So in this case, when you want to invert this, you will get the transpose of that matrix. So you have cos theta minus sin theta and then sin theta and cos theta. That would then be in the alpha beta frame, and then from the alpha beta frame you want to transfer to the ABC frame, and there again you have to transpose whatever system matrix that we used. So that is root of 2 by 3 into 1 and 0. Remember this, when you go from alpha beta to dq, what we had used was I mean ABC to alpha beta, what we had used was root of 2 by 3 into 1 minus half 0 root 3 by 2 and minus root 3 by 2, 1 over root 2, 1 over root 2 and 1 over root 2. Now since we are taking the first column to be the first row, you have 1 0 and 1 by root 2. Since 0 sequence is not considered, that 1 over root 2 can be neglected, and this will now give us your ABC if you put 3 rows here and so on. But then what we are interested in is a per phase equivalent circuit, which means it is enough to consider the A phase alone, and if we are going to consider the A phase alone, we need to consider the first row here, and the first row here is going to be obtained by multiplying this first row by the first column, the first row by what you get here, and therefore that is this column, this term into this minus this term into this. Second row is not really important. So essentially then what you have here is VDS cos theta minus VQS sin theta. The second term that is going to come here, which is VDS into sin theta plus VQS into cos theta, is not important because that is going to multiply 0, and therefore what we can say is that VAS, the stator A phase voltage, is nothing but root of 2 by 3 times VDS cos theta minus VQS sin theta. Right. This is VAS. Now similarly one can do the same thing for IDS and IQS as well. You can substitute here IDS and IQS, same way you transform it reverse in the reverse sense and get back IAS, IBS and ICS. Again we are looking at a per phase equivalent circuit, so it is sufficient to consider IAS alone, and therefore you would have another equivalent relation IAS is equal to root 2 by 3 into IDS cos theta minus IQS sin theta. What we started out with, the equation description here, is the induction machine in the synchronous reference frame. That means a reference frame rotating at synchronous speed. Theta is the angle that the reference frame D axis makes with respect to the stator A axis, and since the frame rotates at synchronous speed, one can therefore say theta must be equal to synchronous speed multiplied by time, assuming that at t equal to 0 the D axis coincides with that of the stator A phase axis. So using this description, then one can try to derive the steady state equivalent of the induction machine. We have done this for stator A phase V and I. Similarly, one has to write down the expression for VDR, VAR and IAR. So once you get expressions for these things, we can try to process it and see whether we can derive an equivalent circuit like representation from this in order to do steady state analysis. So that part of it we will look at it in the next lecture. We will stop with this for today.